Hello everyone, this is Professor Roman. Welcome to the 11th video in my video series on an introduction to discrete mathematics. Today, in this video, we are going to discuss what it means for an argument to be valid. Now we have the necessary background to sort that out. Of course, the first thing we must do is decide what we mean by an argument, and that's relatively simple. An argument consists of a collection of statements, simple or compound, which are the premises or hypotheses of the argument, followed by another statement, which is the conclusion of the argument. So here's the formal definition. An argument is a finite collection, A1 through AN, of statements, followed by a statement. So I just called the conclusion here A. And sometimes I use this notation, but more often I will use a vertical notation. The 3-dot symbol here and the bar here, whoops, I don't think I can do that. The bar represents the word therefore. So you would read either of these as A1 through AN, therefore A. A1 through AN, again, are the premises or hypotheses of the argument, and A is the conclusion of the argument. I said nothing in this definition about truth value. So the hypotheses may be true, they may be false, and we'll discuss that a little bit later. An argument is valid if whenever an assignment of truth values to the statement variables makes all of the premises true, then it also makes the conclusion true. An argument that's not valid is invalid. Now that should be quite a reasonable definition. If all the premises are true, then the conclusion has to be true. That's what makes a valid argument. So let's take a look at some examples. One way to determine whether an argument is valid or not is to construct a truth table. Here's a simple argument. P implies Q, P therefore Q. Here's an example. If today is Saturday, then I do not have to go to school. Today is Saturday, therefore I do not have to go to school. That certainly seems valid. I don't think anybody would argue that. But just as a warm-up, and to verify our intuition, we would construct this truth table, P, Q, and P implies Q. So all three components here are listed in the table. Then we examine the rows of the table to find those rows in which both premises, both hypotheses, are true. And that's only in row 1. I made the hypotheses red so it'd be easy to pick this row out. This is the only row in which both hypotheses are true, and in this case, the conclusion is also true. So by definition, this is a valid argument, as well it should be. In fact, this very simple but important argument is referred to by its Latin name, modus ponens, which translates into manner of placing, which frankly doesn't help much. Let's look at another argument. P implies Q, Q therefore P. Example, if today is Saturday, then I don't have to go to school. I don't have to go to school, therefore today is Saturday. Give that some thought. until it is obvious to you that this is invalid. After all, I don't have to go to school on Sunday. But in order to be certain, we construct a truth table. P, Q, and P implies Q, again, cover the three components, two premises and a conclusion. There are two rows now in which both premises are true, but unfortunately, or whatever, both in the second case, the conclusion is false. So we have true premises, false conclusion. So this argument is invalid. Let's try another one. P implies Q, Q implies R, therefore P implies R. Example, if today is Saturday, then the library is open. If the library is open, then I must study at the library. Therefore, if today is Saturday, then I must study at the library. That also should seem quite valid, and it's worth thinking about that until it does seem that way. Now we have three statement variables, so we need 8 rows. And we pick out the rows where both premises are true. There's 4 of them. And we check the conclusion. P implies R. Happens that in each case, in every case, the conclusion is true. So when the hypotheses are true, so is the conclusion. This is a valid argument known as the law of syllogism. And it was one of Aristotle's main contributions to logic, even though he had a little bit of a problem with infinity. He at least got this one right. Next, P and Q implies R, P therefore R. Now, it again is worth pausing here to think about whether you believe this argument to be valid or invalid. But to check it for sure, we have a truth table. And in this case, the row I've marked here, row 4, shows that the premises can be true, and yet the conclusion can be false. And so this argument is invalid. Sometimes it's possible to determine the validity of an argument without constructing a truth table. And when there are more than 2 statement variables, that can be more efficient. So let's consider this argument. P implies Q implies R. Q, therefore, P implies R. Now we can test the validity of this argument by trying to find an assignment of truth values that makes the conclusion false, but all of the premises true. If we can do that, we have an invalid argument. So we try to force invalidity and see if we can be successful. If we fail, we know the argument is valid. Okay. Well, according to the meaning of the conditional P implies R, this is the conclusion here, in order for the conclusion to be false, it has to be true implies false. P is true, R is false. Now we look at the premises. And the second one is much simpler, so we'll look at that first. In order for the second premise to be true, Q has to be true. So if the conclusion is false and the second premise is true, we must have these truth assignments. But these truth assignments make the first premise false, and I'll let you sort that out. So there's no way to make the conclusion false and both of the premises true. Therefore, if both premises are true, the conclusion must be true. The argument is valid. If all this so far seems to be crystal clear to you, that's terrific. If not, and there's nothing wrong with that, then I would urge you to spend whatever time it takes at each step to make sure that you are very comfortable with this reasoning. Because this reasoning, and it's going to get a little more involved as we continue, is absolutely critical to thinking like a mathematician or thinking like a logical person. Let's look at this argument. R if and only if S, P, or not S. R implies Q, therefore P or Q. In order for the conclusion to be false, both P and Q have to be false. So we're at this stage. Now we check the premises. If P is false, then in order for the second premise to be true, not S has to be true. In other words, S has to be false. So if the conclusion is false, but the second premise is true, we have these truth assignments. Now, why did I go to the second premise? I tried the other ones too, but this one seemed to be the simplest to get sorted out at this point. Okay, could have taken a different course. This involves P and Q, so we're probably not going to get much headway if we try next, after the conclusion falls, to go to the first premise, because we don't have any information about either R or S. We could have said at this point that R and S have to have the same truth value, but we get more for our money, you might say, by looking at the second premise at this point. The order of the premises don't matter, by the way, so you know. Okay, so we're up to this point here. And now we know something about P, Q, and S. So at least we know something about Q here. Q is false. Okay. So in order for this premise to be true, R has to be false, because true implies false is a no-go. So for the conclusion to be false and the second and third premises to be true, we have all four truth assignments. But these truth assignments make the first premise true. So we found an assignment of truth values that make all of the premises true and the conclusion false. This is an invalid argument. Okay. I think here it would be quite difficult to see that intuitively. Now let's consider this argument. If 2 plus 2 equals 5, then the moon is made of green cheese. 2 plus 2 equals 5, therefore the moon is made of green cheese. Well, the first step in deciding the validity of an argument written in English is to translate it into symbolic form. So we'll let P be the statement 2 plus 2 equals 5, and Q is the statement the moon is made of green cheese. We get this argument, which is modus ponens, and is therefore valid. This is an important example because it illustrates the fact that an argument can be valid even if its conclusion is false. According to the definition, all that is required for an argument to be valid is if the premises are true, then so is the conclusion. It says nothing about what happens if one or more premises are false. Okay? And this is critical to understand. Fortunately, it's not an issue. It doesn't cause any problems because in practice, we're only interested in arguments for which the premises are true. So an argument like this, you would say to yourself, well, the second premise is clearly false, so this argument is sort of irrelevant. Okay. But if you want to make the argument for some reason, maybe on some other planet 2 plus 2 is 5, then this is a valid argument. On Earth, it's a valid argument that is useless. And I hope that didn't offend any philosophers, because maybe I'm missing something myself. Mathematically, it's useless. Another argument. If Mr. Jones resigns the presidency, then Mr. Smith becomes president. If Mr. Smith is president, then prices will rise or productivity will fall. Mr. Jones has resigned and productivity has increased, therefore prices will rise. Can you tell whether this argument is valid or not? I think you probably could if you spend a little bit of time thinking about it. But it's more complicated than the previous ones. And while it's a good exercise for your brain to try to sort out whether you think this is valid or not, ultimately, if you have to, let's say you determine it's valid, and you have to convince somebody else, this can be very difficult. You know, you go over the argument, you say, yes, it's valid, and they say, well, I don't see that. Well, what do you say then? What you say then, especially if you have a bet placed on it, is here is the truth table, or here is an argument that shows that this is valid. So let's go through it. First, we get the symbolic form for the argument, and it looks like this. Now, this isn't, a literal word-for-word translation because English is a little, ambiguous, but it captures the meaning of the argument. Well, a truth table is going to have 16 rows because we got four statement variables. So let's see if we can argue without a truth table. In order for the conclusion to be false, of course, R must be false. So let's take a look at the premises. The third one is in many ways the simplest. For that to be true, we have to have both P true and S true. P and S is true if and only if they're both true. So conclusion false, third premise true, we have these three assignments. We must have these three assignments. In order for the first premise to be true, since P is true, Q has to be true. So we can kick this up a level. Conclusion false and first and third premises true, 4 truth assignments. Every variable has to be true. Now we check the second premise, it's false. So we cannot make the conclusion false and all premises true. Okay. So the argument is valid. Before I do some more examples, I want to make an observation that's quite important. Here is modus ponens. P implies Q, P therefore Q. We know it's valid. P and Q represent simple statements, but they could also represent compound statements. We could substitute compound statements for each of P and Q, as long as we do it consistently, so every occurrence of P gets the same compound statement. And similarly for Q, we have something that looks like this. A implies B, B therefore A, where A and B can be any statements at all, simple or compound. This has to be valid. So we have a substitution theorem, our third substitution theorem. We had one for tautologies. That was the first one we had. We had one for logical equivalence. Now we have one for valid arguments. If you have a valid argument and there are some statement variables that appear in the argument, you can replace those statement variables by other compound statements. Whoops. And the argument remains valid. So, for example, this is a substitution instance of modus ponens. P is replaced by P implies not Q. Not only the first P, but the second P, same thing. P implies not Q. And Q is replaced by Q and not R. So we know immediately this argument is valid. This argument is a substitution instance of the law of syllogism. P is replaced by R or S everywhere it appears, in two places, and so on. The law of syllogism is one of the most important forms of argument, and we can use mathematical induction to extend it to more than two premises. So it would look like this. This argument, P1 implies P2, P2 implies P3, and so on, to Pn minus 1 implies Pn. Therefore, the first statement, P1, implies the last one, Pn, that this is a valid argument. So let's prove this by induction. So let P of n be the proposition that this argument is valid for n bigger than or equal to 2. And I'll let you check the P of 2 is true. I should say true here. And P of 3 is just the law of syllogism. So P of 3 is true. If the proposition is true, is the same as saying the argument is valid. Okay. So P of 3 is true. Now for the inductive hypothesis, we can suppose that P of k is true. So this argument is valid. We have to show that P of k plus 1 is true, that we have to show that this argument is valid. I've reproduced the hypotheses here from this previous, from the inductive hypothesis, and added the next hypothesis. And this then becomes the conclusion. Well, to show that this argument is valid, consider any assignment of truth values to the statement variables that make all of the premises true. Okay. Then, if I just select these premises, they're true, all the premises are true, and remember the inductive hypothesis that this argument is valid, we know then that this must be true. P1 implies Pk. So if I replace all of these by P1 implies Pk, That's true. This is true because it appears here. Here is the conclusion. This now has both premises true, but it is just a law of syllogism, and so it's valid. That was actually P of 3. P of 3 is true. Law of syllogism is valid. Therefore, the conclusion is valid. And that's this conclusion. So this argument is valid. P of k plus 1 is true. The induction is complete. We can combine this result, this theorem, with the substitution theorem. Any argument of this form where B1 through Bn are any type of statement, simple or compound, is called a sorites. It's pronounced with a long I and a long E. Sorites. Lewis Carroll, who was the author of Alice in Wonderland, fancied himself a bit of a logician, and he wrote a book called Symbolic Logic, which is kind of interesting. It's still available, I think, as a Dover book. And he constructed a large number of sorites of an unusual nature, let's say. Here is one example. Babies are illogical. Nobody is despised who can manage a crocodile. Illogical persons are despised, therefore babies cannot manage crocodiles. It's worth thinking about this one too. See if you can sort out whether it's valid or invalid just on intuitive grounds. But we'll assign statement variables to these simple statements. Lewis Carroll's argument then looks like this. This argument is valid. And here's another technique for determining validity. Any premise can be replaced by any statement that is logically equivalent to that premise, because those two statements have the same truth value always. So we can replace R implies not S by its contrapositive. S implies not R. And that gives us this argument. Next, we rearrange the order of the premises to give it a chain-like appearance. P implies Q. Oops, where'd I go? Down here. P implies Q, Q implies S, S implies not R, and therefore the first one implies the last one. P implies not R. That's the extended law of syllogism. So this is a valid argument. I have some other Lewis Carrolls. Let's see. Here we go. Here's a couple more Lewis Carrolls. No ducks waltz. No officers ever decline to waltz. All my poultry are ducks. Therefore, my poultry are not officers. No birds, except ostriches, are 9 feet high. There are no birds in this aviary that belong to anyone but me. No ostrich lives on mince pies. I have no birds less than 9 feet high. Therefore, no bird in this aviary lives on mince pies. You know, these are obviously ridiculous, but it might be worth giving it a few moments to see if you can sort out the validity of this argument just by rereading it several times using your intuition, you know now that you have a method for testing validity that always works. You can always make the truth table. This is great power when it comes to evaluating logical arguments. Okay, so obviously it's not very important to know whether this argument is logical or not, or valid or not, but it's critically important to know whether mathematical arguments are valid or not. Okay, so we have finished this section. The next one is a little more technical, Boolean functions and disjunctive normal form. But that's going to be critical for us when we come to the section that follows it, which is logic circuits, where we're going to take a look at the construction of circuits that have various types of behavior. Okay, so thank you for watching the video. I hope you found it interesting, and I hope to see you in the next video.